So in this notebook, we will see how to set up vision transformers or VITs. We'll examine their architectures, and we'll also train a VIT from scratch. Traditionally, transformers have not been used in computer vision. They have been developed in the context of NLP, natural language processing. And in fact, most of the state-of-the-art models in NLP involve some variation of transformers. However, in 2021, it's become increasingly popular to try and port over NLP-style transformer architectures to solve computer vision problems, such as classification, segmentation, and so on. And as of November of 2021, indeed, some of the best performing models in computer vision are based on extensions of vision transformers. So that's been super exciting. How does this work? Well, the high-level idea is to take images and somehow tokenize them. The simplest way is to take image patches, so non-overlapping patches, and treat them as tokens, and then feed it to a transformer type architecture. So that's so that way standard models for processing text can be interpreted as also models for processing images, and as we'll see, they perform really, really well. Some caveats to keep in mind while using vision transformers. So one, quite cumbersome to train, and the number of parameters is typically larger than, say, convnets or SNets of a similar depth. So budget accordingly. The features that you learn in vision transformers are somewhat less intuitive, less interpretable than convnets. Also, while in this notebook we will train a vision transformer from scratch, it's not typical to actually do this in practice. So almost always you train a vision transformer, starting from a pre-trained model where the pre-training has been done over some ginormous data set beforehand, and then just use a vision transformer. Just use your available data set to just fine-tune the weights. So these are some things to keep in mind. Okay, but as usual, we start with importing several things. Most of it is boilerplate, but one special feature here is the INOPS package, which is basically Einstein indexing. So this is used to reshape and slice and dice the tensors that pass through a transform model, just in order to enable better indexing. For this notebook, we will train a VIT on the traditional MNIST dataset. So dataset of 100-digit images, which are of size 28 by 28 grayscale. So we'll see how to tokenize the images and how to perform classification on them. Okay, cool. We'll now dive into the model itself. We'll see how the model actually looks like, but the main thing to keep in mind here, the main distinguishing feature of a vision transformer is the use of the attention mechanism. So attention is basically, we will go through what it is, but really it's sort of a pairwise dot product, operation, right? Followed by a softmax. Okay, and the dot product can be thought of as a lookup between queries and keys. Okay, followed by a softmax, and then finally you synthesize the output tokens using the third transformation called the values transformation. Okay, so QK and V. That is basically an attention mechanism. So a transformer architectures taking this attention mechanism and interleaving with other operations, which we'll go into more in detail. So let's just set up the model first. Okay, and the model is a VIT model with input size 28 by 28. You'll use patch sizes of 7 by 7, which means that there are 4 times 4. That's 16 tokens. So each image will be treated as a sequence of 16 tokens. each input image, and we'll see how that looks. Okay, so that's really all there is to setting up a vision transformer, and this is exactly the vision transformer that was originally proposed, except that since it's a smaller data set, we'll just use a shallower transformer architecture. We'll use depth 4. The actual vision transformer was trained and tested on larger data sets such as CIFAR and ImageNet, and therefore used, I think, 12 or 24 depth networks, or even 32, I think. Okay, cool. So this is how, this is basically the model, and that's all there is. So let's just examine how the architecture actually looks like. So the transformer, the vision transformer architecture takes in an image, a tokenized image, and does the following. So it performs a linear transformation in the beginning, and then you get a bunch of token, a sequence of feature vectors corresponding to different tokens, and then passes it through several transformer blocks. So what is a transformer block? A transformer block is basically, at a very high level, two operations. So the first is the attention mechanism, which, as we discussed, is a softmax of a dot product followed by a linear combination. Right. So that's the attention mechanism. That's the first block of transform. That's the first component of a transformer block. The second component of a transformer block is a shallow multilayer perceptron and an MLP, which combines the different heads of the attention mechanism into and produces the same number of tokens as it started off with. So in this case, the shallow MLP will be just 2 layers with ReLU activations. Okay, so at a very high level, these are essentially all we need. Notice some other features here. So there are several dropout layers inserted all over the place. For this particular data set, we will not need dropouts. I have just set the dropout ratio at 0 everywhere, but the original VIT actually did have lots of dropout. But more interestingly, there's also what's called layer normalization. So what's layer normalization? Just as how we use batch normalization in feed-forward convolutional networks. Batch normalization is a method to stabilize training, and it is basically taking a feature map and normalizing it according to the mean and standard deviation, where the statistics are computed over mini batches. Layer normalization is exactly the same thing. So you take a bunch of tokens and then normalize it by subtracting the mean and dividing by the standard deviation, except that the statistics now are computed not over batches. So it's batch size of 1, you compute it for every sample, but rather you compute the statistics over different heads. Okay, so it's in some sense input dependent normalization. So therefore, unlike batch norm, which is a linear operation, is actually a non-linear operation, which is something interesting about vision transformers. But really, that's all there is, right? So it's just attention followed by an MLP. That's a transformer block. So VIT, our VIT in this case will consist of 4 such transformer blocks. So 0, 1, 2, and 3 stacked up one after the other. And finally, in the very end, to perform the classification, we will throw in a linear layer, which will compute the class probabilities. So that's about it. In fact, let's just also compute the number of parameters in this model. It's about 500,000, a little bit more than that, which is actually considerable for considering that it's just a 4-layer neural network. Okay, so that's really it. And if you want to scale things up, then you simply just increase the number of transformer blocks in this architecture. Nothing. There's not much to worry about in terms of channel scaling or number of or sizes of feature maps and so on. Unlike, say, convolutional networks, fairly straightforward to set up. For bigger architectures, you may have to play around with the dropout parameters to make things work. Okay, cool. So it's just also now train this model from scratch. We'll assume that it is, again, all this is boilerplate code taken from the beginning, from earlier notebooks. So we'll have a training procedure as well as an evaluation procedure. And we'll train only for 3 epochs. Each of these will take several minutes. Unlike say Connet's, number of parameters is so much larger. In fact, there's a quadratic operation happening within each layer, which slows things down further. So therefore, compared to a connet of a similar size, transformers will take much longer to train. So this will take a few minutes. Okay, so that took about 8 minutes of training. As you can see, accuracies have been going down. In fact, they went down quite quickly in the beginning and kind of marginally improving since then. We are already up to like nearly 96, 97%, which is quite high, which is for 3 epochs of training. If we train for longer, assuming we'll do better. Okay, so overall, how do we do? Let's divide it on the test set. And about 96.47%. Good. So there you go. Vision transformer and how to train it from scratch.